Okay, good afternoon, everybody. This is Maths 465, and then this week we have 2.7 and 3.1 due this Friday. Any question about homework?
Do you mind going over 3.113?
All right. Any other question? 3.113. All right, I'll do. Let me see the question. The logistic distribution is associated with the CDF, cumulative distribution function, and find the PDF of the logistic distribution and show that its graph is symmetric about x is equal to 0 or y-axis. So let's see. Logistic, okay. Number 13. The logistic. Logistic is there's no parameter. The cumulative distribution function is given as 1 over 1 plus e to the negative x. Okay. Well, this is same as writing e to the x over e to the x plus 1. Okay, either way, x is anything. As you can see, when x goes to infinity, then e to the negative x goes to 0. Okay, this is going to 0, so this is disappearing. So 1 over 1, that is 1. Okay. When x goes to infinity, this is going to 1. And also, if x goes to negative infinity, then this negative x goes to infinity. So e to the infinity is going to infinity. 1 over infinity is 0. So satisfying the conditions of cumulative distribution function. Okay. So now, what is a density function? Density function is derivative of the cumulative distribution function, always. So probability density function is a derivative of the cumulative distribution function. We simply differentiate this guy, okay? And then this is equal to, I'm gonna use this guy, this guy. So this derivative is a negative of this derivative, that is a negative of e to the minus x. Do you see? And then divided by this square. So 1 plus e to the x minus x squared. This is a 1. So simply this is e to the negative x over 1 plus e to the minus x squared. This is the probability density function. And this x can be anything. So again, this is any number. And you need to show that this is symmetric about the y-axis. That means this is an even function. Okay? This is an even function. So plug in negative x for this. Negative x. Negative x is here. So this is e to the x itself divided by 1 plus negative x. So this is e to the x squared. Oops. Okay. To see that this is equal to this, okay, this is equal to this, I divide every term by e to the, well, multiply by e to the negative x, okay, squared, okay, squared. Numerator and denominator, we multiply by e to the negative x squared. Well, this is actually e to the negative 2x. So 1 plus e to the x squared, okay? Then what do you see? The numerator is e to the minus x, is that right? Okay, this time this is e to the negative x. Dividing by, multiplying by this is multiplying by this, e to the negative x inside. This times this, yes? This times 1 is e to the negative x. And then e to the x times e to the negative x is 1, okay? And then this is squared. Oh, this is equal to f of x itself. Okay. So this is an even function. So f is even. So the graph is symmetric about the y-axis. Okay, that's it. Make sense? All right. Any other question? Okay, if you don't have, then I shall move on. We're in section 3.2. Okay, we're in section 3.2. And this section is a little bit, yeah, not a little bit, but pretty much new. Okay, new. We are using gamma function. Okay? If you have heard about gamma function, then that's fine. But if not, then we study. Okay? Because we are learning, so we have to learn new things. Okay? New things. All right. Then last time I introduced gamma function. Do you remember this gamma function? Gamma function is defined by gamma of this t can be anything, x or y or whatever. And this is defined by integral from 0 to infinity of y to the t minus 1 n times e to the negative y. Okay, dy. Okay, this is a gamma function. T is positive. One more time. It is a gamma function. Gamma function. Gamma function, gamma of t is defined by integral from 0 to infinity. This is a definite integral, but the t is here. Okay, this is a variable t. Y to the t minus 1 and e to the minus y, and then dy. With respect to y, we integrate. So that means that this y can be anything. This is x, this is u, this is whatever you like. But this is t, this is a variable. And this integral exists for a positive t. Okay? If t is 0 or less, and this integral does not exist. And then we have derived the properties of this one. Yeah, let me show. Okay, let me show one property. Okay, then gamma of t. So t is greater than 1. Okay, t is greater than 1. Then we can get the integral by using the integration by parts. Okay, this is y, and then t minus 1. Okay, and then times c to the minus y dy. Okay, then integration by parts. Okay, integration by parts. So what is the idea? I like to differentiate this and then integrate this guy. Okay, that's the idea. So differentiate and integrate. So this is a f and a g prime. Okay. So this is same as writing y to the t minus 1 and times the integral of this. This is negative of e to the minus y. Okay, and then this is from 0 to infinity. 0 to infinity. Minus of 0 to infinity of the derivative of this. This is t minus 1 n times y to the t minus 2. And then integral of this guy is this, the negative e to the minus y dy. Okay, you agree? I'm using the integration by parts. Okay. And now t is greater than 1. Okay, so this is positive. And then plug in infinity. Okay, and this is going to be infinity. But this is negative, e to the negative infinity is 0. Okay? But which one is larger? Larger means which one is more powerful. Then this is powerful. So when you plug in infinity here and here, it's going to be 0. And also 0 comes here, then it is 0. Okay, this is 1. So this part is 0. Okay, this portion is 0. Okay, that's the 1. Well, if you're not sure, then you can use the L'Hopital's rule. Okay, L'Hopital's rule, and then see that this part is 0. Now, what is this? This is t minus 1 goes outside, and also this negative goes outside. This is t minus 1 times of 0 to infinity of y to the t minus 2. T minus 2 is, yeah, okay, t minus 1 minus 1. Okay, I shall write this way in dy. What is c? What is this integral? This is the gamma function's value at t minus 1. T minus 1 is here. This is a constant, so this is t minus 1 times gamma of t minus 1. Okay, so this is a recurrence relation for the gamma function. The gamma of t is equal to t minus 1 times gamma of t minus 1. Using this identity, you can evaluate the value of gamma function. For instance, you're going to have gamma of 1. Okay, gamma of 1. That is simply 0 to infinity of gamma t is 1. So this is 0. Okay, 0. Y to the 0 is 1, of course. E to the negative y, dy. But this is the negative e to the negative y from 0 to infinity, right? Then infinity, then this is 0, 0, then this is 1. So this is equal to 1. Okay. So gamma of 1 is 1. And then together, we use this guy, this guy. Then when t is a positive integer, okay, positive integer. So for instance, when you like to have gamma of 2, then this is using this formula. This is 1 times of gamma of 1. This is 1 also. Gamma of 3. This is 2 times of gamma of 2. Okay, this is 2. And then you can write this is 2 times 1 or 2 factorial. So in general, gamma of n, okay, n. This is n minus 1 factorial. Okay, n is a integer. Okay, so that's what we can have. So please get used to gamma function. If you're familiar with gamma function, then you're good at this section. Also for other math, like yeah, statistics, 565 you can take, and also 455, that's Fourier analysis. Okay? So you can be good at those guys. Anyway, don't hate the new stuff. The new stuff is interesting most of the time. So you should love them, and you should be good at math. Okay, that's what I like to see from you. All right. So then we have defined the gamma distribution. Can let me define again. Gamma distribution. New distribution. Gamma distribution. Okay. So gamma distribution is this. Our notation is this. The random variable x is subject to the gamma distribution. This gamma is not same as this guy, but just the name is gamma. And then two parameters, alpha and theta. Sometimes other textbook may be beta, alpha and beta. This textbook is using alpha and theta. Okay. This is a gamma distribution. This is a gamma distribution when the density function is given. Okay, density function is given. So density function is of this form. F of x is equal to the fraction 1 divided by gamma of alpha. This gamma is a gamma function. Okay? And alpha can be any number, not necessarily integer, kind of 1/2, 2/3. Any number is fine, okay? but positive, of course. And also this is positive. And then times the theta to alpha. to the alpha, n times x to the alpha minus 1, and then times e to the negative x over theta. Okay, this is a density function. And then in this case, x is positive. And then, of course, alpha, theta are positive. These are fixed numbers. And then x is the only variable. And if when x is negative or 0, then necessarily the value of this is 0. So I don't want to write just x is positive. This is indicated. X is positive, then this value. Okay? Note that this is a constant. This is some number. And then variable is here. X is here, also x is here. Okay. Then if you remember, we defined the exponential distribution. Okay, please note. Note exponential distribution, exponential of theta. Well, maybe I capitalized first one. Yeah, doesn't matter. And in this case, did you remember the density function? I don't remember. Okay, I don't remember. Do you remember? 1 over theta to e to the minus x over theta. Remember this? X is positive. Then I compare this guy with this. Okay, compare this guy with this. We have this common part, e to the negative x over theta. Yeah, this is it. And then theta to the denominator here, theta to the alpha. So alpha is 1, right? Alpha is 1. Compare, this is 1. 1. What is 1? Gamma of 1. Do you see? Gamma of 1 is, oh, actually this is 1. So then we can rewrite this guy as 1 over gamma of 1, and then theta to the 1, and then x to the 1 minus 1, and then e to the negative x over theta. Do you agree? We can write the exponential distribution's density function like this: gamma of 1 times theta to the 1 and x to the 1 minus 1, because this is 0, x to the 0 is 1, and then exponential part is this, same as this guy. Then what is this? Alpha is 1, and then theta is theta. So this is gamma of 1 and theta. Do you agree? Okay, i.e. Exponential distribution is a special case of the gamma distribution with parameter alpha is 1 and then theta is just theta. Okay, please note. Exponential distribution is a special case of the gamma distribution. Okay, this is important. Gamma of 1 theta is exponential distribution. Okay. All right, then this is a one we have to note. Okay, and then we like to show that gamma distribution has the moment generating function something. Okay, so this is one. Okay, first one. This is the second part. This is just a note. Okay, we like to remark this is the case. Exponential distribution is gamma of 1 theta. The next thing is a moment generating function. We like to derive this guy. Okay, and then this is given by 1 minus theta t to the negative alpha, and then t is smaller than 1 over theta. Okay, we need to show this. This is actually problem number 327. But we like to derive this. Okay, let's prove this guy. This is problem number 327. Okay, and then unfortunately there's no solution given. Proof question usually that are not given. Can you see this? Okay, I'm not in a rush, so let's see this actually. And then this is not so hard. Well, this is interesting, maybe. Okay. So let's consider. By definition, this is equal to integral expectation. This is the expectation of e to the dx, right? And so this is equal to density function is given by this, and this is the density function. So we're going to use this. This is 0 to infinity of e to the tx, and then times the constant 1 over gamma of alpha, and then theta to the alpha, right? And then x to the alpha minus 1, and then e to the minus x over theta, and dx. And this is a moment generating function. Then here's an idea. Okay? Change a variable. Change a variable. Let y be. I don't know why this is the case, but this is a way it goes 1 minus theta t, and then times x over theta. Okay, this is a change of variable. This is the idea. Just a simplifying, okay? Simplifying the situation. Not a great idea, but just an idea. Change of variable. Okay. So what is dy? dy is equal to 1 minus theta t over theta and times dx, right? This is your 1. And also, try to solve for x. Can try to solve for x. X is equal to 1 minus theta t, and then on top is theta y. Do you agree? And this is 1. I solved for x. X is equal to y divided by this. Okay? X is y divided by this. And also this guy. And then when x is equal to 0, y is equal to 0. When x is infinity, then this should be infinity, because we are restricting t be smaller than 1 over theta. T is smaller than 1 over theta. This is always positive. So when x is infinity, then necessarily y is infinity. So 0 to infinity is not changed. Okay. So then m of t is, this is again 0 to infinity, and then e to the tx, that part is well, x to the alpha minus 1, that part is um, right. This is a theta y over 1 minus theta t. This is x, and to the power alpha minus 1, and then times the e to the negative y. And when you combine these two guys, okay, okay, then you can see that it's going to be just e to the negative y, as you can see. Okay, e to the negative y comes because this times this is using this guy, okay, simply. So that's what this is. And then also we have to take care of the constants. Constant is this 1 over gamma alpha and then theta to the alpha. Okay. And then dx part. Okay. Dx part is this. That means we have theta theta over 1 minus theta t. Okay. And times dy. Okay. dy. X is this guy. So differentiate dx is equal to, this is a constant times dy, right? And then so this is it. And this is it. we can rewrite like this, and then this is a constant, so go outside of the integral gamma of alpha theta to the alpha, and another part theta to the alpha minus 1, and then y to the alpha minus 1, and times theta, and also this guy. So this guy is 1 minus theta 2 is t is here, also 1 minus theta t is here. So to the power alpha minus 1 times 1, so this is going to be 1 minus theta t to the alpha. You agree? Yeah, this times this. This to the alpha minus 1 times this. And then what else? Theta to the alpha minus 1. And then another theta is here. So this is theta to the alpha. Okay? Theta to the alpha minus 1 times theta. Theta to the alpha. And then y is a variable, so we can't take this out of the integral. So 0 to infinity of now what? Y to the alpha minus 1 and times e to the negative y and dy. They agree? Then this is gamma function's value, gamma of alpha. Okay? And then you can see that we can cancel this and this, also this and this. Remaining one is this guy, only this. So this is a 1 minus theta t to the power negative alpha. Okay? So this is the one. First step is this. And then second and third one, we like to see that mu is the average or mean is alpha theta, and then sigma squared is variance is alpha theta squared. Okay, we like to show this. And then this is a problem number 3 to 10. Number 3 to 10. All right. Now we have m of t. This is easy. Okay, 1 minus theta t to the negative alpha. So what is derivative? Negative alpha times this to the negative alpha minus 1, and times this derivative is negative theta. So we have this as, okay, negative alpha times 1 minus theta t to the negative alpha minus 1, and times the derivative of this part, the negative theta, so is equal to alpha theta and then 1 minus theta t to the negative alpha minus 1. Okay, so you can say mu is m prime of 0. Okay, plug in 0 is 1 to the anything is 1, so alpha theta is quick. Okay, and also we need the second derivative. Second derivative is derivative of this guy, so alpha theta times alpha minus negative alpha minus 1, and times 1 minus theta t to the negative alpha minus 2 times the derivative negative theta. Okay, so this is equal to alpha theta squared, and then 1 minus theta t negative alpha minus 2. Okay, so I don't think so. I forgot alpha plus 1 here. Okay, sorry, alpha plus 1 is here. Alpha times alpha plus 1. Okay, so the sigma squared is equal to m double prime of 0 minus mu squared. Yeah, this is equal to plug in 0. And this is 0, so this is 1. So we have alpha plus 1 times theta squared minus this squared, alpha theta squared. Okay. Now alpha squared theta squared, alpha squared theta squared, that's going to be gone. So we only have alpha times theta squared. Okay. So these are obtained. Mu is alpha theta, and then sigma squared is alpha theta squared. Please memorize this too. Oh, by the way, your textbook has this information. Yeah. This is your textbook, right? And then this is a cover, backside of the cover. Yeah, discrete distributions. Okay, you have Bernoulli, binomial, geometric, and so on. Okay, on the left side, right side, you have continuous one. Okay, continuous distributions, beta, chi-square, exponential. So you can look up this, and then try to memorize everything. Okay, so that's my advice. All right, so we have figured out the moment generating function of the gamma distribution, and then using that we can derive the mean and variance very quickly by simply differentiating those guys. So do you have any question? So these are the exercises, but a very nice exercise. So let's move on. And as I mentioned, the exponential distribution is a special case of the gamma distribution. That is alpha is equal to 1. Okay. Theta can be anything. Gamma of 1 theta is exponential of theta. That's what we did. All right. Examples. Let's text example 325. Example. Number is not so important, but I'm taking the example from the textbook. Okay. This is y is subject to the Poisson distribution with the parameter 2. Okay. If you remember, then a gamma distribution is derived from the Poisson distribution. So I'm kind of repeating that idea. And then x is a waiting time. The waiting time. Waiting time in minutes. Okay, minutes. In minutes until fifth call arrives. Okay. Or fifth customer, whatever. Okay, fifth thing will happen. And then in this case, alpha is equal to this 5. Okay, alpha score. So alpha is equal to 5. Alpha is equal to 5. And then theta is 1 over lambda. Okay, this is lambda. Okay, lambda. And then theta is it's reciprocal. Okay, 1 over lambda. So that's going to be 1/2. That's the way it goes. So necessary x is subject to the gamma distribution. Okay, gamma distribution of alpha and then theta. And this is the one. And then alpha this case is 5, and then theta is 1/2. So this is the distribution of the random variable x. This is a gamma distribution. Then density function is what? Can you figure out density function? Okay, but by the formula, okay, 1 over gamma of alpha is 5. Okay, 5, and then theta is 1/2 to the power alpha, that is 5. Okay, and then times the x to the alpha minus 1, 5 minus 1 times e to the minus theta is 1/2. So this is x divided by 1/2. Okay, this is a 1. Okay. I'm just using the formula. Okay. Then I'd like to ask you, what is gamma of 5? Gamma of 5 is 5 minus 1 factorial, 4 factorial, right? 4 factorial. Well, this is 24. Okay, 24. Well, you can write 4 factorial. And this is 1/2 to the 5. So this should be on top, 2 to the 5. Okay, 2 to the 5. So 2 to the 5. And then denominator is 4 factorial. Okay. And then we can say this is x to the 4th, right? X to the 4th. And times e to the minus what? Dividing by 1/2 is same as multiplying by 2. This is e to the negative 2x. Okay. So this is a density function. Okay. Then can you tell me mean and variance? Okay. Mean is you have to memorize. Mean is alpha theta, sigma squared. Variance is alpha theta squared. So you have to memorize this guy. Alpha theta, alpha is 5 and theta is 1/2. So it's gonna be 5/2. Okay. And then sigma squared is alpha theta squared. So this is equal to, one more time, we multiply by theta. Theta is 1/2. So you see that this is 5/4 quickly. Okay. This time theta is 1/2. So this times 1/2, 5/4. Okay. These are the ones we can derive. Then next step is we like to see the density functions graph. Okay. What the graph look like? That's what the question. This is the exponential function times the polynomial, or x or something. So the graph should be something like this, something like this. Going at 0, it is 0, so 0 starting from 0, and then going up and then going downward. That picture. Well, special cases, this is 0. Okay, this is 0. Then I mean x to the 0. Then this is 1. So only exponential function is affecting. So let me see. Well, let's see the graphs of exponential function or density functions of the gamma distribution. Okay. Well, the effect of parameters alpha and theta. There are two parameters, right? Alpha and theta to the graphs of density functions. So let's fix the theta to be 4. Okay? Theta to be 4. Then alpha varies. Okay? Alpha varies. Then what is the graph of the density functions? And so this is x, of course, and this is y. Then origin is this. When alpha is equal to 1, okay, alpha is equal to 1, alpha is equal to 1, then this value is 1. So as I mentioned, this is x to the 1 minus 1, that is 0. Only exponential function is appearing. So that means this is a minus f. Okay. Alpha is equal to 1, some number, and then going down. This is an exponential function. So going this way. Okay, this is the case. Alpha is equal to 1. Okay. Alpha is equal to 1. Alpha is equal to 1/4. Okay? Alpha is equal to 1/4. This is 1/4. Then this is x to the some negative number. So when x, excuse me, alpha is equal to 1/4, then the graph is going to infinity as x approaches 0. So graph goes like this, something like this. And then this is a graph, okay. This alpha is equal to 1/4, smaller than 1. Then I go into infinity as x approaches from the left. Otherwise, if this is positive, then a graph starts from the origin, because x to the positive integer, positive number, then it's going to be 0. So starting from this point, and then a graph goes like this. And so this is a graph, okay. Alpha is equal to 2, then this is the graph. And then alpha is equal to 3, then something like this, okay. This alpha is equal to 3. So this is the effect. Alpha is smaller than 1, then a graph approaches infinity when x goes to 0. And alpha is equal to 1, then starting from some point here, and then a graph is just an exponential function. And otherwise, the exponents of the x term is positive, and starting from the origin, and then going upward, and then somewhere afterward, it's going to be decreasing. Okay? Increasing and decreasing, increasing and decreasing. That's a graph. All right, then next case is alpha is now fixed to 4. Okay, alpha is fixed to 4. Then a graph goes like this. Observe. Alpha is 4 means this part is 4. 4 minus 1 is 3. So this is x to the 3 all the time. So always starting from the origin. Okay? Origin. And then theta is smaller than, it's going to be go upward very quickly like this. Theta is smaller than up here and then decay like this. This is the graph. Theta is equal to say 5, 6. 5/6. This is the graph. And then theta is equal to 1, then this is going to be something like this. And then going downward like this. Okay, so this is a graph. I'm not good, but this is the idea. Theta is equal to 1, theta is equal to 2, then more moderately like this, something like this. Theta is equal to 2. This is the idea. I will not ask you to draw a graph, okay? But yeah, you should know. You should know this. Even if you can't draw, but you can tell the difference. Right, this is a graph. These are the graphs of the density function. Okay, and then next one is another special case of the gamma distribution. One special case was the exponential distribution. Other case is chi-square distribution. Chi-square distribution. So that is defined by x is subject to the gamma distribution, and then the theta is 2. Okay, this is fixed. Theta is fixed 2. Okay, this is a condition. Theta must be equal to 2. And then alpha must be a multiple of 1/2. Okay, 1/2. Cannot take any number, but a multiple of 1/2. So this is of the form r divided by 2. Okay, r divided by 2. And then this r is a integer, positive integer. 1, 2, 3, 4, 5, those integers. So this is actually a multiple of 1/2, r times 1/2. And this is denoted as chi squared of r. Okay? Chi squared of r. And then r is a integer, 1, 2, okay? 3, any integer. That's a 1, and then we're going to denote this as chi squared of r. You will see that this is a degree of freedom. R is the degree of freedom. And then also you will see, after we study the normal distribution, okay, a random variable that is subject to the standard normal distribution, and that is squared. X is say, or y is say subject to the standard normal distribution, and that is squared, so y squared. That's going to be chi-squared of 1, chi-squared of 1. If there are r random variables, those are subject to the standard normal, and then they are independent, then a sum of those r random variables must be subject to the chi-square of r. Okay? That's the meaning of this. We'll see. Okay? So chi-square is a kind of square of normal random variables. Okay. Then can you tell me the density function f of x? Can you tell me? Yeah, of course. This is gamma of alpha. Alpha is over 2. And then theta, this is second one is theta to the alpha. So theta is 2. And then 2 to the r over 2. And these are the constants. And then times the x to the alpha minus 1. This is alpha. So 1/2 alpha r minus 1. And then e to the negative. Theta is always 2. So x over 2. And this is a density function. And again, x is positive. So this is our density function, okay? And then in this case, we say x has a chi-square distribution. Chi is a chi, not chi. This is chi. Chi-square distribution. Chi-square distribution with r degrees of freedom, with r degrees of freedom is a name. Okay. The chi-square distribution with r degrees of freedom. Okay. So this is the definition. As I mentioned, r degrees of freedom is this can be equivalent to the sum of all independent standard normal random variables. So there are r freedom, r degrees of freedom. That's the meaning of this. Okay. I shall explain in the next section, probably 3.3. I shall explain. So once again, x is chi-squared of r. Okay. Then can you tell me the moment generating function and also the mean and then variances? Can you tell me? So what is the moment generating function? Tell me, please. When you have m of t is gamma of alpha theta, then it's gonna be, remember this, theta t to the power negative alpha. Okay, please don't forget. Okay, this is the one. Gamma distribution alpha and theta, then it's gonna be 1 minus theta t, and then to the power negative alpha. So this is alpha is 1/2 alpha, and theta is 2, so will be what? 1 minus theta is 2, so 2t, 2t, into the negative 1/2 r, right? This is a moment generating function, and then this case t is smaller than 1/2. Make this guy as positive. Okay? This is positive, so necessary t is smaller than 1/2. Okay, can you tell me the mean? Mean is alpha theta. Okay, this times this, right? R over 2 times 2 is going to be R, right? What about the sigma squared? This times theta. Okay? This mu times theta, so 2R. Okay, 2R, you can tell. And then one more thing is what is cumulative distribution function f of x, capital F of x? Cumulative distribution function. Yeah, this is simply integrate the density function. That's all. Okay, so this is from 0 to x of gamma 1 over this function, gamma of r over 2 and times 2 to the r over 2, and then times x to the 1/2 alpha r minus 1, and then e to the minus x over 2, and then dx. Oh my gosh. What is oh my gosh? I should use the other symbol, right? Not x, but say, do you like y or w? Okay, I'm going to use w. Okay, sorry, this is w, this is w, and dw. Okay, sorry, this is w, and this is w. We can't use x. Okay, x is here. Okay, so w, sorry. And then again, this is x is positive or 0. Okay, x is negative, then f of x is capital F of x is 0. So this is these are the ones. Okay, please memorize. Okay. Not only math, but many academic fields need memorization, knowledge. Memorization is a knowledge. If you know more, then you're better. Don't stay, but absorb new stuff, and then get your knowledge bigger. And that's gonna be your kind of property. Okay. So example 326. 326. X is subject to the chi-square distribution, and then degree of freedom is 5. And this is given. Then we like to get the probability that x is between 1.145, and then 12.83. Equity sign doesn't matter. So let's say equity signs are here. How do you get these values? This value. And then there's an answer. Yeah, we need a table. There's a table for chi-square distribution. So let's see. Look up the chi-square distribution. Okay. Otherwise we can. Chi-square distribution table is somewhere. Standard number. E distribution. Or chi-square is what is the F distribution? What is the chi-square? Chi-square. Oh, right here. Page 100 and 501. Page 501. Look up page 501. There's a chi-square distribution table. Chi-square distribution table. So this is the one. Okay? This is the one. Chi-square distribution table. Page 10500. You can't see clearly, but these are the degree of freedom. Okay? These are the degree of freedom. So starting from 1, 2, 3. In this case, we have 5. 5 is here. And then I'll look up the number given 1.145. Yeah, that is here. 1.145 is here. And look up this number, 0. You can't see, but 0.050, 0.050. And then that is indicating the value area over here. Okay, this is the one. 1.145 is somewhere here, 0 to 2, 1 point. And then this part is a very small part. How small? 0.050. Okay, area 0.050, only 5%. Okay, and then another number is 12.83. Okay, 12.83 is over here. Okay, this is our number, 12.83. Okay, this is 12.83 is somewhere here, right? Okay, and then this side area is 0.975. Okay, that's the meaning of this. So what we see is, to get this number, this is x is smaller than or equal to 12.83. Okay? This minus x is smaller than or equal to 1.145. Okay? This is what we have. And then this is obtained as 0.975, I think, 975, minus 0.050. Okay? 050. As you can see, as you observe, then this probability is 0.975. This probability is 0.050. So difference is 1. This is 0.925. 925. Not much numbers are given, just special numbers like this: 0.050, 0.5, 0.9, okay, 9, and so on. Very, very special numbers are given, because we can't have the table for each degree of freedom R. Okay, 1 to 0, 1, 2, 3, 4, 5, up to 100. Oh no, we can't have that many. So very special numbers are given. So look up the table on page 501. Okay, this is the only way. Another example is okay. So also get the probability that x is greater than or equal to 15.09. Okay, this is the one. This is 1 minus of probability that x is smaller than or equal to 15.09. Okay, or just take the complement. Of course, equality sign is removed, but that's okay. You can take this equality sign. And this is 1 minus. Look at this number from the table, then that's going to be 0.99. You can tell 0.99 is this probability. And then, so this is equal to 0.01. Okay, these are the answers. Always look up the table, and then you can tell. We have some minutes. Yeah, I like to show how to read the graph. So here's the one. X is subject to the chi-square distribution with the degree of freedom R. Okay, and then the alpha is between 0 and 1/2. Okay, alpha is between 0 and 1/2. Okay. Then the number chi-squared sub alpha of R. Okay. This is not indicating the distribution, but this is actually a number. Okay. This is a number such that, okay, this is a number such that the probability that the random variable x takes the value greater than or equal to this number, chi-squared sub alpha of R. Okay, and then this probability is alpha. This is a definition of this number. What? Actually, what? And then if you see the picture, then you will see clearly. the graph of the density function is something like this. Okay? Consider it this way. My picture is not good, but this is the idea. Okay. Alpha is between 0 and 1/2. So somewhere here we have a number, and then this region's area is alpha. Okay, that's what this is. Okay, this region's area is alpha. Okay, this region's area is alpha. Then this point, okay, this point is the one. This point is the one. This point is no, I don't think so. Other way around. So okay. Alpha is not greater than or equal to 1/2. So this point, this region's area is alpha. Okay. Then this is your point chi-squared sub alpha of r. Okay. X is greater than this number. X is greater than this number. So then this portion's area is alpha. Make sense? This portion's area is alpha. Then that number, this number is chi-squared of sub alpha of r. X is greater than that number. That portion's area is alpha. Okay, that's the meaning of this. Then this side area is alpha. Then can you tell this point? This point, this is our chi-squared sub alpha, and then r. This point is, you will see this is 1 minus alpha of r. Okay. The reason is here. You'll have some minutes. Okay. Right. Here's an interpretation. Okay. Chi-squared sub alpha of r is the 100 times 1 minus alpha's percentile. Well, alpha 100 minus times alpha 1 minus alpha. So this portion, okay, this portion's area is 100, well, 1 minus alpha actually. And then in the same way, you can see that 1 minus alpha and then r. Okay, this is 100 times alpha, okay, this percentile. Okay. So these are the ones. So smaller than this guy, okay, smaller than this point, and this portion's area is alpha. And that number is 1 minus alpha. This is alpha. This portion's area is alpha. Okay, so this is the one. So necessary, okay, necessary. This is a definition. Okay, this is a definition. Now, if we use the opposite inequality, less than or equal to chi-squared and then r, but this is 1 minus alpha. Then this is also alpha. Okay, so this is the one I want to tell you. So please memorize these two guys. Okay? This is a definition of this number or this number. Okay, this is a picture. This side is alpha, or this side is alpha, and then this point is chi-squared sub alpha of r. This point is chi-squared sub 1 minus alpha, and then r. You can use these guys and then figure out the probability that x is between some number. And always those numbers are given in the table. Okay? Otherwise, we can't figure out. We need a computer to figure out those numbers. Okay? But I'm going to ask you only those special numbers. And then probably during the exam, you can use a table. Okay? You can use a table, chi-square table or normal distribution table. Okay? So that means you can see the textbook. Oh my gosh. That's not what I intended to, but yeah, actually you can. Well, that means the test will be not so easy, okay, a little harder, because you can see the textbook, okay. Any question? Do you have any question? Okay, then lecture is done. And then if you have questions on homework, then you can ask me. You can stay and ask me. Otherwise, you can leave and then have a nice day.
You too. Have a nice